In this video, I'd like to demonstrate the design of a simple contingency plan using the colored Petri nets. What you can see in front of you is the model that we're going to use to show how 3 database failures or server failures will be dealt with by a contingency plan that has 2 checks to be made on the network and 2 repair actions. I would like to start by, instead of describing this structure that you can see visually, I'm going to show you the syntax of the actual domain-specific language we designed to build contingency plans. If you have a look here in the middle, this middle piece here is the main part that we're interested in. Start with a statement contingency plan, or contingency, that takes 2 arguments, failures and fixes in this case. The 2 arguments are the starting input state and the output state. So the contingency plan will take information it finds in the failure state, run the plan, and then produce output in the fixer state. So it's designed to, of course, fix a failure. Inside the block here, you'll see we have got 2 check statements and 2 repair statements. These matched the check and repair that we see over here. The ones in red are the checks and the blues are repairs. Let's start by looking at a repair. We would like to repair the network. We've modeled that the duration of this repair will take 5 time units. Once the repair is completed, the next thing to do is go back to the server access check. Let's look up at the server access check over here. The server access check says that if the check fails, we need to have a look at the network access first. So if we're unable to access the server, the first thing to check for why that is true is a possible network failure. We haven't modeled what to do if it passes. So if the server is accessible, because we haven't stated that in this line, that means if the server is accessible, we'll move automatically to the exit state here, which means we've fixed it. So how do we decide if it's a pass or fail? Have a look down the end here, the match statement. We've said the server access check will pass if we match the text fixed. So if we find that the token flowing around this contingency plan has the text fixed in it, well then the server is accessible. So if it does not have the text fixed, then of course the server is not accessible. Have a look back at the server access here. I'm going to drill down into the component that this actually represents. Here it is. It is the token switch component that we described in a previous video. What we can see here is the input state is check server access, contains some failures here that we want to model, and I said match fixed. To pass it, we must match fixed. There it is, there's the text, token matches fixed. We'll get down to the pass state. If not token matches fixed, we fail. And if we look at these input text, the word fixed is not here anyway. So we know that the first time we run this, all of these tokens are going to fail and go down to the failure state. Look back at the overall network. The failure state is modeled with a state here called server access fail, which feeds into the network check. Look back at the DSL here. I just said I'm making a check called network access, and if it fails, we're making a check called the server access, and if it fails, move directly to network access. I didn't have to talk about transitions and states. I did not have to use the terminology of the colored Petri net. I used the terminology of a contingency plan with the words contingency, check, and repair. So this state over here, the server access fail state, was filled in for me. Why is there no server access pass state? That was because it was told to use the whole plan's pass output, which in this case is the fixes state up here. How did we tell it to use it? Quite simply, we specified a failure option on the server access, but we did not specify a pass option. I could have said that. Pass fixes, like this, but, and this fixes of course matches the fixes up there defined as the success output of the entire contingency plan. But I don't need to do that. By not specifying a pass state, it defaults to the pass state for the whole plan. That's very convenient. If we look at the next check, we'll find we have specified a pass state and a fail state. So when we check the network access, if this check fails, then we need to move on to the repair network. If the check passes, then we need to move on to the repair server. So what we're saying with this statement is, if the network is at fault, then repair the network. If otherwise, repair the server itself. How do we tell the difference between whether a network or a server failed? Well, we just simply said the network failed if it is not the network. Have a look at this in the actual model here. We check the network access. Let's drill into that. Check network access. Fail the network access if the token contains network. So the word not meant that the match for network was put into the fail state. If I had said match, it would have put it into the pass state. Let me repeat that just to make it clear. I said not here. If I had said match, like I did on the previous line, then it would have passed the network check if I had network failure inside the text. So what I'm basically saying is I wanted to fail it based on that text instead of passing it. And that's correct. So the repairs we've talked about, the main thing that we've missed here is what do the repairs actually do? Well, in this case, I've used the code prefix to say prefix the token with the text fixed. Then we'll find when we go back up to the server access, it will match fixed and we'll pass back up to fixes. Let's run this and see how it works. Watch this. Let me pause it quickly. So it ran really quickly. What you saw happening there, actually let's reset it and run it step by step because that was a bit too quick. So I'm going to step it through one step. Bang. We fired the server access check and we saw that the first failure, network off, failed the check. So it came down to the server access fail. If I fire this again, it's going to run through the network access check and we'll see. Will network off fail the network access check? Well, it should fail it, right? So it should not go down to network access pass down here. It should instead go up to network access fail. Let's run that transition. Bang. Yes, indeed, it went to network access fail. So the next thing it will run into is the repair network. And of course, the repair network will add a fixed statement to it and put it back up here in the failures. Okay. Now we see here that we've fixed the network off problem, but we'll see that it's also put forward in time, so before that this token can recheck and end up in the fixes, we'll end up modeling a service stopped token. Let's run that one. Okay, the service stop token failed the server access check. Now it's going to check the network. Let's try that. Yes, the network access passed because it wasn't a network problem. So now we need to repair the server. And we repaired the server. So now we've got two of these problems repaired. The next token to run will be the disk failure. Notice that the time on this fixed server stopped one is quite large. 52 compared to 5 and 6 over here. Why is that? That's because we modeled that the repair server action should actually take 50 seconds. So this token is not going to be rechecked until after 50 seconds. It takes much longer to repair a server than to, for example, repair a network. So let's occur the next one. Oop, now the disk failure has been checked. Boom, that also went down to network access pass, and boom, up to here. It's been fixed. So we had to repair the server twice, repair the network once. So two of these have got big times on them and one's got a short time. So run again and bang, we see that we've double checked the server access now from the network, and that went up there. And the next one, and the next one. All three problems fixed. Going back to the syntax over here, we'll see that matches exactly the DSL we've done here. Problems in the failures were moved all the way to fixes through the route implied over here. And we did not have to specify any more than this. The only thing we have specified in addition is a layout, just so that we have positioned all of these components in a way that looks nice on the screen. What I didn't discuss was some of the input stuff over here. The most important one is the state failures, where we've modeled these three failures to occur at 3 different times. And of course I've also done a little bit of extra modeling here with states called help and fixes and fixing. The reason for that will be discussed in another video. But if you look back at this thing here, I've got a help and fixing thing here. What are these for? This was because we're about to build a more complicated network that says, what about the case where a repair is not possible, it requires bringing in external help? Then we need to, for example, post from one of these repair statements. When we double check here, if the server is accessible, it still fails, even after it's been fixed, because there's an additional problem. Then we need to post it out to help instead of to fixes. We can demonstrate those more complicated contingency plans in a follow-up video.